started just yet, so, you know. We've still got 3 minutes for the rest of everybody to show up. Thank you. This is the one we don't want. Yes! We finally figured out the light system. Good morning, everyone. How is everybody? Good. Enjoying your second week of the rest of your life? Any questions before we get started? We're a touch behind, of course, because, you know, we will perpetually be a touch behind in this class. So I'm going to try to motor through a fair amount of material today, so hold on to your butts. Yes? What does the colon mean? Well, why don't we just get into the slide, shall we? Last time we spoke, we introduced the idea that we can organize a program using the visual metaphor of a flowchart, and today we're going to start off by seeing several examples of this, as well as examining various bits and pieces related to the manner in which we program. So, it's very, very highly important to have a good concept of what's going on with respect to memory manipulation. I've said it a few times already, but I'll say it again just to drive the point home. Variables in a program do not behave the same way as variables in algebra. In algebra, your variable is variable. It may represent any of a number of different values. In a program, a variable is always a particular set of memory cells residing somewhere in the hardware of your computer system. As such, the memory cells which compose a variable may only be in either a 0 or a 1 state, because binary and hardware and stuff. So, a variable will always have a concrete value, regardless as to whether that concrete value is meaningful. So if you declare a certain amount of memory and you don't initialize it with anything, that memory actually continues to hold whatever was used whatever the operating system was using that memory for previously. It just retains those previous values. In the absence of the context of the previous program, that memory is meaningless. So we consider it junk or garbage data. However, just because it's junk data doesn't mean it doesn't have one specific value. So much for the concept of a variable. They are variable because the values vary throughout the execution of the program, not because they represent multiple values at once. Does that make sense? Hopefully. So, assignment is your basic operation of memory manipulation. It's very simple. On this side, you specify the memory cell that is getting the new value. On this side, you specify an expression which the computer calculates. The calculated result is stored in the indicated variable. You've already seen me use this in that program that we did previously, and we'll see a few more examples of it going on. Assignment is definitely something you'll want to come to grips with fairly quickly. It's like, if you were learning how to write, it would be like knowing how to actually form a character, as opposed to composing words, which is more like composing the program. Anyway, so the notation on this slide is slightly strange with respect to programming in Python. In fact, in most, if not all, C-based languages, the symbol which is used for assignment is just one equals sign. This is somewhat different from algebra, where a single equal sign indicates equality between two expressions. We actually have an operator which tests equality between two expressions, but that is denoted by a double equals sign, not a single equals sign. Single equals signs are assignment. So, as your colleague pointed out, what on earth could be the purpose of this colon character? Why are we deviating from Python's syntax on this slide? Well, in the mathematical abstractions which describe program operations, this is the symbol that is used. So, over your careers as computer science students, you will encounter the same concepts presented multiple different ways. Sometimes it will be in the syntax of a different language, sometimes you'll know how to do things one way in Python, a slightly different way in C, a slightly different way in Java, probably a much different way in Haskell. And in addition to all of these sort of compilable languages, you will also be required to pick up the mathematics of programming. This is the symbol used for assignment in the mathematical meta-language of programming. So, when you see it in future, that's assignment. However, only a very few actual programming languages use the colon equals notation for assignment. These tend to be programming languages in which assignment is not a common operation. These are the languages that like to minimize the amount of internal state that they hold. The only one that comes to mind is Lisp. Has anybody heard of Lisp before? Anybody know what Lisp stands for? Lisp processor. So Lisp is, you can kind of think of Haskell as being Lisp 2.0. But anyway, Lisp is a very, very old language. I think it predates C, actually. But anyway, so that is the purpose of the colon. In Python, we have supported multiple assignment. So you can put multiple assignment statements on one line. E is assigned to X, F is assigned to Y. Aside from the occasional example of this in the slides, I actually don't think it's terribly useful for people who are sort of entry-level programmers to use this type of notation, as it can just be confusing, and, you know, this is unnecessary most of the time. You can perform swap operations in one line this way, but we'll see an example of that later on. You're going to have to shout.
When you're assigning a variable, do you use colon at the equal sign, or is the equal sign just
In Python, just the equal sign.
All right.
If you're writing a formal proof of correctness for a program, the mathematics that you express that proof in will use the colon equals. Does that make sense? Question?
I believe you can also use the colon equals in Python.
Oh, can you?
Recently added in 3.9 or something. As a
Polar side, it's a special
It
operator.
turns it into an assignment expression. So it'll return the value that's being assigned.
It's only
But
valid
I
in some
haven't gotten that
contexts.
to use it.
Yeah,
So it's
okay.
like if statement and stuff.
Okay. Bloody Python. We're not going to be covering that for obvious reasons. Yeah, so yet again, Python has added something and given it slightly different semantics than would make any degree of sense. So, you know. Anyway, so let's examine the following program, expressed as a flowchart. The purpose of this program is to calculate the the median of three numbers, x, y, and z. So we can accomplish this with a branching tree of, what are these things called? They're conditional expressions, yes. In this case, if-else statements. So we can, in fact, produce a reasonably cogent example of this. We can actually translate this directly from a diagram to an algorithm expressed in Python. For those of you who have laptops open in front of you, the useful and appropriate thing to be doing while I'm coding on the board is to also be coding the same algorithm on your computer, hopefully in a way that you can compile it. This is called live coding, and it is considered current and useful code teaching pedagogy. So we will create a median function. It will take x, y, and z. We note that the first thing we encounter in the program is an if statement with the conditional x is less than y. So we say if x is less than y, we do something, otherwise we do something else. Oh, got the numlock. There we go. Yes. Okay, I'm going to have to kill the lights a bit more. How's that? Better?
Yeah.
Good. Thank you. So, nobody go to sleep, okay? So, in order to denote in Python, let's follow this branch for the time being. In order to denote that this is on the path leading from this conditional. In Python, we tab that over by one space, or by one tab error. We then write the new if statement in there. So if z is less than x, that also has an else branch, like so. Inside of this, on the true branch here, we have the variable m being assigned to x. Otherwise, we have another if statement. If z is less than y, then m is equal to z, else m is equal to y. You guys see the structure? Are you beginning to see the matrix? Question?
Why can't we just use another if statement? Or an else if statement?
In which case?
Else if the...
Well, we're already using quite a few else ifs. I'm not sure I understand what you...
An elif statement?
Oh, elif.
Yeah.
Well, because we haven't covered them yet. Let's try not to jump too far ahead of the slides. So, going on the other branch, if x is less than z, then m is equal to x. Otherwise, if z is less than y, m is equal to y, else m is equal to z. And then, because, although it is not obviously stated in the flowchart, it's reasonably obvious for anybody with any degree of common sense that m is the intended output of this function. It's even stated so in the question. So, in order to actually return, or to actually pass on the results of this calculation to the whatever program is calling this function, you must explicitly return it with a return statement. Return m. If you do not include this statement, you will get every question on every assignment wrong. In order to write an algorithm, you must specify the input and you must specify the output. Everything is input and output. This is computers. Okay? So, if we want to test that, we can say, give me the median, show me the median of 3 numbers randomly drawn from my brain. There we go. And we execute that Python 3 topic1.py. And the median is 6. So, there we go. Similar procedures can be used to calculate the, the maximum or the minimum or other similar things. Are there any questions? I raised the lights to see if anybody has any questions. Okay. So, at the back there? Yes, that's very likely. Bring it to tutorial. You probably have a syntax error. Yeah. An unexpected end of file. That means that you didn't close the thing off properly. So I can't fix everybody's syntax errors during lecture, or else that's the only thing we would be doing. So a couple of points, just quickly. Taking a look at this program, and I know it's like faded again, but the indentations are extremely important, all right? In Python, you tell what's inside of what via indentation. This is in contrast to some other programming languages you may have used, which will typically use curly braces or something like that. In Python, the spacing carries important semantic weight. So if you mess up the spacing, you will mess up the algorithm. Makes sense? Hopefully. Good. So, I'm going to skip that. You can put more information on a flowchart than you need, but it makes it cluttered. That's the gist there. What is the maximum number of operations required to compute the median of three numbers?
4.
Exactly. How do you know that?
I see 4 boxes
Yes.
on a line.
Another way of stating that is that that's the maximum depth of any branch of this tree. Right? So let's consider a different example. This is an algorithm which computes both the minimum and the maximum of a series of incoming integers. Or possibly floats. But it says integers, but it would work for floats anyway. So, inputs. We have a series of temperature readings, Ti, for I between 0 and some number n. So we have n temperature readings. We also have some integer n, which is greater than 0. Our outputs are the minimum and maximum of that series of temperature readings. So this is the structure of the algorithm. You'll notice, first off, that this is not just a simple branching if statement tree. This is our first real concrete example of a loop, right? Notice that execution flows back up to before this conditional in this flowchart. Therefore, that is the loop conditional. All right? So, essentially, we set the data up here at the beginning. We set the initial values of maximum and minimum to the first element received, the first temperature reading received, because if you only ever receive one temperature reading, it is both the maximum and the minimum, so that's correct. We also set a variable I. The only purpose of the I variable is to be able to access t of I at various points, right? We need to be able to step through the temperature readings in sequence. This is what's known as a counter variable. Right? And the thing that it's counting is how far you are through the data structure. So, unfortunately, this one requires a little bit more knowledge with respect to data structures than you've yet been introduced to, but perhaps it's a good, preview of coming attractions, shall we say. So, def min max takes a series of temperature readings. I'm going to call that capital T, and some integer n. Now, because this is a data structure in a very technical sense, we can actually derive the size of this just by calling a function on the data structure. However, to keep consistency with this flowchart, I'm going to just take n as an input in this case, right? So, first things first, I is equal to 1, min is equal to the first element. The way that you denote the first element is using angle braces. So, for those of you who have used other programming languages, you may think it's strange that we have not declared this input as being a list or an array or any of the data structures that you're used to. This is just how Python do. It is an array or a list or a tuple because it is used in that manner inside of the function. This is what we call polymorphic typing. Python does its very best to hide the idea of typing at all. Like it's not like it doesn't do type checking, but it does everything in its power to prevent you from knowing that there's even type checking going on unless you hit an error. So, you know, it's, again, one of the ways in which I find Python kind of silly. But, you know, it is what it is. Anyway, so, while I is less than n, we do the stuff inside the loop. This is the stuff inside the loop. This last statement is particularly important. Without it, the loop will run forever. We are waiting to reach the end of a data structure. If we never increment the I variable, we will never reach it. So, it's actually my recommended approach when you're writing a while loop to start, like don't wait until you've written the whole rest of the loop before you add the thing that's actually going to get you out of the loop. Just put that in at the beginning, and then you can add the actual functionality of the loop above it. So, if t at I is less than the current minimum, we set that minimum equal to ti. Otherwise, if t at I is greater than the current maximum, the maximum is equal to ti. And what do we do for the else branch for this one? Call it out. Nothing. Good. So there we go. And then, of course, what are we outputting in this case? Minimum and maximum. So return minimum, maximum. Print. So, yeah. I'm going to assign a data structure, let's say D, and make it a list. It's going to be a series of numbers. There we go. Print min max D, and just because I'm lazy, I'm going to use a function which gets the length of D because I just don't feel like counting them. And bing, bang, boom. Uh-oh. Am I missing a brace here? I am missing a brace. Yeah. So expected, that's that same syntax error that you were having back there. Basically, that means that I have mismatched parentheses, right? So I open 3, but only close 2. Very common error, very easily fixed. Just add the missing parentheses, and boom! So our interval, our minimum is -8, and our maximum is 35, which can be confirmed through easy inspection of the data by a human. Now, this is only easy to do because there's only, maybe 15, 20 numbers in that list. If there were 15 to 20,000 numbers in that list, this guy would be able to process that in a small fraction of the second, whereas to find that as a human being would take much, much, much longer. Are there any questions about that example? Cool. Way at the back, you're going to have to shout.
Will we be allowed to use type annotations using Python 3.9?
You're permitted to use type annotations if you know how to use them, but we're not going to teach them. Yeah. So it is possible to ask very politely for Python to use particular types in particular places. However, it's not enforced, and therefore not a proper type system. Question?
Is the output a tuple?
The output is a tuple.
Okay.
This is again sort of implicitly what Python does when you ask to return multiple things that are comma separated. It just kind of implicitly puts some braces in there and returns it as a tuple. But we don't know what tuples yet are because we haven't covered them in class yet, have we? Question?
On an assignment, can we just use like the sort function on the list, or is that not allowed?
Well, it kind of depends on what the question is asking you to do. If the question is asking you to write a sorting algorithm to sort the list, then if you just call sort, then you're probably not going to get many marks. But yeah, in general, we don't want to be overly restrictive of the types of functions that you can use. So if you think that it's useful to sort the data, sort the data. Another approach to this problem would be to reorganize this data structure so that it went from smallest to largest. Then you just take the front element and the back element, and that's your minimum and maximum. That would be an alternative approach to the problem. It's less efficient, though, to do it that way, because to sort it requires more computational complexity than to simply just go through it one by one. We're going to see these types of concepts a little later in the course, but I just thought it would be, it's like, yes, but it's slightly less efficient. Any questions? Good. So I'm just because we're behind, I'm gonna skip a couple of dumb questions. Yes. I'm assuming all of you can count. So what's the maximum number of comparisons? You guys can figure that out yourselves, I guess. Yes. So let's move along. So we're going to talk in more general terms about programs, and then we're going to get to topic 2 probably next time. But this is important, this is important knowledge. So we've talked about algorithms quite a bit. I've shown you some implementations of algorithms in Python, but we must also now examine what on earth a program is. So the very first thing I have to do is to correct everybody's grammar. I have noticed a disturbing trend of people referring to a program as a code. This is disgusting to me. It is not proper English. When you write a series of instructions that compose a something, that is a program. A code is something that you use to encode a program. All right? So it's not a code. If I see anybody saying, hey, could you take a look at a problem I have with this, with a code that I wrote over here, that is, I'm going to first correct your grammar, and then I'm going to help you. So anyway, programs are encoded in computers that can execute these programs automatically. That is the purpose of the machine. We have a distinction between fixed and stored program computers. A computer does not necessarily require a software component. In fact, many computers are built exclusively from hardware components and do not have the ability to be programmed. Think of my traditional example of a kitchen timer, right? No way to program that thing. All of its functions are encoded in hardware elements, right? Nevertheless, it is performing computation. It is executing an algorithm, right? However, that algorithm is not encoded in programming code. It is encoded in hardware components. So, the earliest computers such as the Manchester Mark I, were fixed program computers. They performed one calculation. In the case of the Manchester Mark I, if I'm getting my history correctly, this was the machine that they used to break the Enigma machine during the Second World War, leading to a campaign of misinformation which allowed the Allies to misdirect the Nazis as to the location of the D-Day landing, thus securing a bridgehead in Europe and leading to, at least the Americans arriving in Berlin at approximately the same time as the Russians. So, one could make the argument that the Soviets had broken the Nazis' spine prior to the Americans showing up on the scene, but not that this is a history class. You'll get this, it's just part of my charming personality. So, anyway. Oh, pardon me, it's a stored program computer. Pardon me. So, prior to the development of the stored program computer, you're looking at things like Charles Babbage's analytical engines, which were mechanical, like marble machines that performed calculations, which is kind of cool. The early history of computation is very cool, but anyway. So, stored program computer. This means that the computer itself can have different sets of instructions loaded into it. Obviously, this was a much more powerful and dynamic technology, as stored program computers are what we think of as computers these days. So, one of the big innovations was to store the program in the same way that the data is stored. This allows manipulation of a program in the same way that we manipulate data, which was a key innovation. It allowed allowed computers to run programs which modify their own programs. This was an extremely important development in the history of computation. We've already talked about the von Neumann architecture, but the memory unit, it should be noted, stores both program instructions and data. So when your CPU executes instructions, those instructions are being fetched from the memory unit in the same way that the data it's operating on are being fetched from the memory unit. Modern computers have a memory hierarchy of caches for improving performance. You have a large number of different types of memory available to you, depending on the situation that you're in. Generally speaking, I think we already talked about this, but maybe we didn't. There's a trade-off between the speed of the memory and the permanence of the memory, right? So the faster the memory is, the faster the values in that memory decay. So memory actually is subject to decay when, external radiation hits memory cells and just, random events of the universe. Basically, the bits get flipped over time. This eventually scrambles and corrupts the data to the point where it's no longer even useful. And depending on which bit it happens to, it can be a big problem to only have one bit flipped. Basically, with very fast memory, such as the type that's used in the CPU itself, that memory has to be refreshed, on the millisecond or nanosecond scale in order for that memory to remain cogent. Memory that is stored on what we consider permanent media, read-only memory, ROM, that is SSDs, flash drives, magnetic drives, data on those types of devices can remain cogent for, 10, 20 years. It's surprisingly short how, it's surprising how impermanent computer memory actually is. Like, it's not, at some point you should print all of your photos. If you want your grandchildren to see them, you should print your photos at some point. Because CD-ROM, I think, only lasts about 50 years before it's unreadable. And that's one of the more permanent ones. So, did you learn something? Good. So anyway, CPUs operate on bits, zeros and ones. Bits are electrical signals which are existing inside of the hardware. 0 indicates 0 volts, a low level voltage. 1 indicates usually 3.3 or 5 volts, depending on the voltage that the architecture runs at. These are grouped into words, typically 32 or 64 bits. Laptops, typically 64 bits. Cell phones, typically 32 bits. The word size of the operating system was one of the key ways in which technology was improving in through the 80s, 90s, and early 2000s, or noughties, or whatever you want to call them. My favorite comparison with this is the evolution of Nintendo consoles. So, if you consider the Nintendo Entertainment System, that was an 8-bit machine, right? So, that's why the Nintendo Entertainment System could only support 256 colors, right? That's because 2 to the power of 8 is 256. And they were using 8 bits to indicate the color of a pixel, and that's where you get that, right? Same thing with the sound, right? Sound could only be expressed in 8-bit values, so that's why you get like this very, that's where chiptune comes from. It's just low compression on the terms of the number of bits used to store the waveform. So we jump to the Super Nintendo, which was a 16-bit operating system. So if you know anything about the difference between a NES game and a SNES game, one of the things they were really enthralled with in the early days of SNES games is the fact they could represent all colors that they could possibly want, because they had 16 bits to do so instead of 8. So that's why they're all very colorful. Also, you had, vast improvements in sound synthesizer and all kinds of other things. Incidentally, on the Game Boy, only 4 possible color values were possible per pixel, which meant that they were using 2 bits for each pixel on the Game Boy, which is kind of fun. But anyway, so then we move to the Nintendo 64. 64-bit operating system. We now have the ability to perform floating point arithmetic, which enables 3-dimensional modeling, right? Because you can't do that without, it's not like it didn't have the capability of floating point, but like, generally speaking, before you hit 32-bit architectures, floating point operations had to be accelerated by dedicated hardware modules. So basically, in the NES, floating point is virtually unheard of. In the SNES, you see some of it, but really, by the time you get to the N64, floating point is everywhere. Yes?
Do you know if the developers of this game actually had to work with this machine language like a bit, or if they just had a language that they could use?
I believe that Nintendo games were written in assembly code, or something close to it. If you take a look at the Nintendo Sound font, or the Nintendo Sound format files, those are definitely, like, chiptune is coded in assembly code, basically. By the time you hit the NES, you definitely are working with some kind of compiled language. Yes, question?
NES was assembly, SNES was also assembly, N64C.
Ah, well, there we go. We have an expert in the room. So, there we go. Assembly languages are still technically a compiled language. Anyway, what are we talking about here? Yes, CPUs contain their own very limited memory known as registers. Your main operations on registers are to load data from memory, to perform some either arithmetic or logic operation on the data in registers, and to store that data from registers back into memory, and to jump to another instruction based on the value of the data in a register. So you have to imagine, and I really wish I had a chalkboard, but imagine you have two spaces of memory, right? You have program memory and you have data memory. The first three operations are operations on data memory, right? The CPU maintains a register known as the program pointer. The program pointer tells you which instruction you're on in instruction memory. Jump operations are manipulations of the program pointer itself, not of the instructions. So basically you just, you say, oh, I'm on line 6, 7, 8, oh, I'm going to jump to 12, okay, jump to 12, okay, back to 13, or back to 1, okay, back to 1. That's kind of the flavor of assembly languages. Assembly languages are terrible to work with, just so you know. So, Fortran was an early high-level language from 1958. Fortran stands for Formula Translator. On these older machines, programs were programmed on punch cards. So this was prior to some clever boffin hooking up a typewriter to a computer and thereby getting the keyboard. It was also prior to the existence of the cathode ray tube, which was eventually adapted into monitor technology. So you have to imagine computers in this era operating primarily on paper. So they would read holes in paper, and they would make holes in paper that you would read as binary code encoding the results of something. So that's this is the era that we're talking about for computing, right? This, by the way, is an if statement. So if you were, a computer programmer in, 1952, you would spend several weeks with a hole punch and a stack of punch cards punching your program out, double check, triple checking it, making sure that you didn't make any mistakes anywhere. You would carry this huge stack of punch cards over to a slot on one side of the machine. You would trip, your punch cards would go everywhere, and if you hadn't labeled them, you had to start all over again. So, the point of all of this is that you should appreciate the era in which you live. So, from there, we get languages like ALGOL and Pascal in the 60s and 70s. In the early 70s, you also have the development of C and the proliferation of C-based languages in the following decades. While graphical programming languages have a dedicated use, textual languages are dominant for large programs. You may have, has anybody used, I think it's Scratch, where you click together the code blocks? No serious programmer will ever program in Scratch because it's not fast enough, right? You do occasionally see text, graphical languages in, some obscure domains. The controllers that go into industrial automation equipment, for example, are sometimes programmed with a language that is meant to resemble electrical schematics, primarily because the people programming those things, which are called PLCs, are electrical engineers that don't necessarily know how to program programming languages. So they made a nice language for them that looks like something they're familiar with, and that's what they use. It's called ladder logic. You do see graphical languages every once in a while, but it's kind of like how all of you eventually will be you'll be expected to know how to use a command line interface, right? To use your operating system. It's like you've got normies who have to click around with a mouse, right? And then you've got Chad programmers who know how to do stuff very quickly and mostly get the operating system to do all the stuff they need to do for them without them even asking. And that is what you'll learn in 1xC3. So I've already talked about that. I'm going to skip this slide. So, differences between programming languages from a sort of top-level perspective. Question?
I just have a quick question. Was Linux always more powerful than Windows, or was there at some point it surpassed Windows?
So Linux was originally based on the Unix operating system, so it started off on the right foot. It took a while for it to become as popular, and basically usefulness is dictated by how many programmers are creating programs for the operating system. So as it became more popular, it became more useful. But because it started off with better bones, it's just a better operating system and has attracted more people over time, basically. Like, for example, like 95% of servers are running Linux, and anybody who's got an Android phone is also running Linux. So, Linux is the world's most popular operating system, if you count phones. So, anyway, so in programming, we have this it's a very specific what's meant by high and low level language. What high and low refer to specifically is the level of abstraction of that language. So abstraction roughly corresponds to how many assembly or machine code instructions correspond to each line of code, roughly speaking. But it also is, you sort of fold into that the types of mathematical abstractions which are available to the programmer. So, for example, C, which does not contain any object-oriented language semantics, is a lower-level language than Java, which does have object-oriented. Java is a lower-level language than Haskell, which is based on the functional paradigm. This is not to say that high-level languages are better than low-level languages. They are different tools for different purposes. You cannot, basically, if you want to optimize a program, it is impossible to optimize it any further than to intelligently optimize it in assembly code. Assembly code, optimized code, is the very fastest thing that can run on a computer. As opposed to, Python or Haskell, which make it easy to write programs. Like, the thing about assembly is it's very difficult to work with. Question?
So you said that each programming language, like how high level it is, it depends on the number of instructions of assembly, right?
Roughly speaking.
But I know like most programming languages, they have like C functions that you can call like anyways.
Mm-hmm.
Yeah, they integrate like C libraries. They can use stuff at an even lower level.
Yes, right now I'm not talking about what the programming language is doing under the hood, right? I'm talking about the language that is presented to the user, right? So if you take a language like Haskell, for instance, a large number of operations occur per character that's in that file, relative to C, where there is comparatively fewer object code instructions that are executed per character in that file, right? Does that make sense? Like, even if Haskell is using a bunch of C language constructs under the hood, how many is it using with respect to how much code you have to write? Does that make sense? Okay. Any other questions? Okay. Thank you very much, everybody. See you.